Hello and welcome to our first webinar. This is Cohort 3 and we're going to be looking at tricky topics and misconceptions in number and algebra. In particular, prime numbers, highest common factor and lowest common multiple, recurring decimals, so that's the number side of it. We're going to be looking at proportional change and a bit of kinematics. So that's a bit of algebra and number. So some of these I would normally have done in the first session, but for some bizarre reason I thought, no, I'll switch it around so that I'll do the harder stuff when you can see me so that we can discuss things face to face. However, I think perhaps it was a little too much for your first session because some of the indices and surds stuff that we were doing on a very general basis, which would be really going in towards AS level. So don't panic too much. Hopefully your first few weeks have been okay in school, and at any time that you want to say anything, please just interject. If there's anything you don't understand, just say, and if you're happy, we'll start. Okay, so, a little starter. A perfect number is equal to the sum of its divisors. So what that means, so divisors are the numbers which divide into it, which we also call factors. And what it's saying is, if you imagine, well, I'll show you an example. The smallest perfect number, 6, 1 times 2 times 3 equals 6, and 1 plus 2 plus 3 equals 6. So it's a perfect number because you can multiply the numbers and add the numbers and get that same number. So I want you to have a quick think. What is the next perfect number? And I should have said you're going to want a pen and paper to be able to scribble things down, work things out. So if you think you've figured that out, when you figured it out, put your hand up. And you do that by just clicking on the bit where the little hand is. Great, excellent. We'll wait until I see a few more hands. Okay. So, Matt, you were first. What
is it 28?
Yes.
All the multiples are 1, 2, 4, 7, and 14.
Yeah, excellent. It is 28, and in fact there are only 4 perfect numbers between 1 and 3 million. So you were lucky I didn't ask you what the next one was because it would take a while. So if you were feeling really mean and you just wanted to waste a lesson, actually is what it would be. You could get them to do the next one. But this is just the sort of starter way, just getting the kids to think about the relationship between adding and multiplying, and it sort of gives them a sense of the size of numbers, and that these are really, really rare. So they'd figured this out in ancient Greece. They'd obviously spent a lot of time, well, with nothing much else to do. The 5th one wasn't found until sometime around the 1400s, I imagine, which was 33,550,336. Just getting the students to tell each other what that number is could take up a load of a lesson. Being able to read numbers, like reading all maths, is something that can cause quite a bit of confusion, especially without commas. Now, there's a bit of, I'm just going to go a bit off on a tangent at the moment to talk about commas because, there's a debate about to use or not to use, really. I would, in this sense, it's quite difficult, isn't it, to figure it out. And I think I feel a natural tendency to want to put commas in. But it can cause confusion with the students, especially if they start to think that it's a decimal point, or they're putting commas in the wrong places and not really understanding what they're used for. So it's worth investigating, what you think and what you prefer to do, and talking to the students about what they prefer to do. Anyway, there are more perfect numbers. So they found 43 perfect numbers. So the last one was found in 2005 and has, what's that then? 18,340,103 digits to it. 4,000 pages of A4 to write down. Thank goodness we have computers now. Oh no, sorry, 2013, they have found 48 things. Would help if I remembered my slides. Just madness. Anyway, that's just a little bit of madness that you can share with the kids. Prime numbers. So we're going to start. Sam, sorry, do you have a question, or is your hand still up from before?
Sorry, it's still up.
Oh, that's right. Okay, so the the prime numbers. Something that students at a certain age, it seems to stick with them, but for a while they just forget what you're talking about, and the weaker students often struggle to really pinpoint the difference. And it's funny because to me it's very innate sense of what a prime number is. To them, it's just another thing. They might have this strong sense as they do for odd and even numbers, but not quite the same sense when it comes to prime numbers. So, why are they prime? I'll ask Mark, as I asked you first of all. Mark, why are they prime? What does prime mean? Have you got a microphone, Mark? Because we cannot hear you if you are talking.
How's that?
Oh, perfect. Yes, that's working.
Oh, there you go.
There you go.
So I didn't have it set up right. Yeah. Basically, they're prime because they can only be divided by themselves and 1.
Exactly. Yeah. So, each number has only 2 factors: the number itself and the number 1. So, why is 1 not a prime number? Matt?
I think the definition of it is it has to be greater than 1, and that comes from some theorem of arithmetic. Every positive whole number can be written as a unique product of primes, and so if 1 was included, then you couldn't have a unique product, because say 15 is 3 times 5 and 5 times 3, but then you could have 1 times 5 times 3, 1 times 1 times 5 times 3, so there would never be a unique product.
That's an excellent explanation. That is absolutely correct. And the explanation that I give the kids is that, and it is a similar thing in terms of the definition here that we've got. So if we're saying the prime number has 2 factors, which is the number itself and the number 1, I sort of say to them 1 is not a prime number because it hasn't got 2 factors. It's only got 1 because the number itself is the number 1. But if you've got a higher ability class, then explaining it as you've just done, and actually that will make, what you just said will make much more sense than later when they have understood, as we're about to do, about composite numbers. And it's difficult, isn't it? Because you're like, well, which comes first? I suppose that you have to talk about prime numbers first before you get to composite numbers. And then you can come back to this question. and get them to sort of think about why thus one is not a prime number, because otherwise that would mean that all our composite numbers, Euclid's theorem about writing it in a unique way, would just be impossible. The students often ask, as I put there, what is the thing about prime numbers that people obsess with? And as you saw when I showed you that clip of Marcus de Soto, he is obsessed with prime numbers. And of course it's because they are the basis for all the composite numbers. So they are the basis for all numbers going forward and effectively set up our number system. And I know that a lot of people also talk about, in terms of engaging with the students' interests, the code breaking possibilities, and nowadays the software data security. So for online banking and those sort of things, and the sort of sending keys that are prime numbers. So the finding ever increasingly large prime numbers means that you can better encrypt things. If you're interested in that, and you haven't read it, then Simon Singh's book, The Code Book, is excellent, and one to recommend to the older kids as well. So, just a little bit for starting the kids off with prime numbers. And I've uploaded a sheet that's got this onto Student Central. It's something called the Sieve of, and I do not know how to pronounce his name, Aratishinus. Anyone know? I have no idea. But he was a Greek who came up with, basically just wrote all the numbers out in a grid and went through them crossing out 1, all the multiples of 2, all the multiples of 3, all the multiples of 5, all the multiples of 7. So obviously he knew the basic primes. And what occurred was, so he crossed out the 1, crossed out all the multiples of 2, except 2 itself, crossed out all the multiples of 3 except 3. So he left the prime numbers, and effectively by doing this, and you can get the students to do this themselves, to cross out all these multiples, it ends up, you get them to highlight the ones that are left, and you're left with all the prime numbers up to 150, which is very nice. They can then see those. And I think I probably have quite a, you have a strong sense of what's prime up to about 50, and then after that you sort of think to yourself, oh, sending 5 into it, and over 100 you're having to sort of think a bit more about it. But it's really good for them to be able to see all of those primes. So that's quite a good one just to get them started into it. This is now extension work. It's just going off to just develop you a bit more and tell you a bit more about things. So Euclid, who we were talking about before, who really developed a huge amount of maths, initially thought that 2 to the power of n, take away 1, would be prime for all odd numbers. So you replace the n with an odd number. So 2, 1 is prime, 1 is odd, so 2 to the 1 minus 1 is 1. Okay, that's a bit weird because that's not really prime. 2 to the 3, for example, is 8, minus 1 is 7, so that is prime. But aside from the one that I've just done where n is 1, can you disprove this for another value of n? If you have to think about it and put your hand up. Okay, so Matt, you put your hand up first again. So I'm going to click on you once more, and then after that I will not do that again. But Matt, how do you disprove that?
I've come up with 23. 23 times 2 is 46, minus 1 is 45, and 9 and 5 go into 45.
So actually this means to the power of n. So the slightly raised
sorry.
superscript means do it to the
I'll
power
go back
of
to the
n.
drawing board.
That's all right. Mark, how about you?
I'm assuming I think I might have balled this up actually looking at it, but is it something as simple as to the power of 4, or is it 3? You've got 2 times 2 times 2 so it gives 16. Obviously minus 1 is 15, which is divisible by 3 and 5.
Yes. Do you know when I did it? What did I do? No. Yes. So because 2 to the 4. Sorry, for all odd numbers. N. So n should be an odd number.
Right. Yeah.
Yeah,
No, I
that's
have
fine.
brought it up. Yeah. Fair one.
That's all right. We'll get there. So keep going, trying odd numbers. It really helps to have a calculator as well, I should have said, shouldn't I? Pen, paper, calculator. Does anyone come up with one? Well, I was just thinking 2 to the 5 is 32 minus 1. I think that should be. Sam, were you going to say something? So you.
I was just going to say, I think it works for the smaller numbers, which is what we're all working through. It's just got to be something bigger, is it?
Yeah, I think if you try 11, that might. I think I remember trying 11 because I thought, I'll jump in somewhere a bit higher. 2 to 11 is 2048. We take 1 away, 2047, which I can only assume is prime. But actually, I think if I put the 5 in, oh no, look, I did do 2 to 11. There you go. Oh no, it's not prime. Sorry. We thought they were prime. So yeah, so we've been coming up with prime numbers. 30. Well, yeah. So 2 to the 5 gives you 31, which is prime. 2 to the 7. 2 to the 7 is 100 minus 127. That's prime. So 2 to the 11 is not prime. So yeah, it is a case of just working through it. So often, this is just with disproving things, often you can just keep trying things until you find something that doesn't work. I got myself in a muddle as well there, thinking about what I was trying to do. I'm trying to show it's not prime. So 2047, although it looks a bit prime, is actually 23 times 89. But it'd be tricky to then work that out, wouldn't it? You'd have to know that you could divide something into that. As we saw, this is the video that I showed you, and I've just put it in here. That's the one that I showed you where he's explaining it to Alan Davies. You know, there are infinitely many primes where you take a number of prime numbers, multiply them all together, add 1, and thus you've created a new prime. So we can continue to do that. And I imagine that in terms of creating new primes, they've just got enormous supercomputers that are multiplying all the primes that they already know and adding 1. But just to do that multiplication with the countably infinite primes that we already have must be taking absolutely ages. So although if I go back, although 2 to the n minus 1 was not always prime for odd numbers, he then thought perhaps there was a link between the perfect numbers, you know, the ones that we were looking at all the way back here, the ones where they add together and times together gives the same answer, and those first 4 perfect numbers were actually generated by this formula, where P is each is a prime. So when he put in P is 2, 2 minus 1 gives us 1, so 2 to the 1 is 2, 2 to the 2 is 4, so 4 minus 1 is 3, times 2 is 6, and put P is 3, you've got 28, and put P is 5, you've got the next one. So those first 4 perfect numbers that we looked at before were just generated by this formula and the first 4 primes. So you then must have thought, brilliant, this is absolutely great, try P equals 11, and unfortunately, if you put P as 11 in, you get 2 to the 10, 2 to the 10 is 1024, 2 to the 11 is 2048, minus 1 is 2, minus 1024 is not a perfect number. It's 2,096,128. But if I add those together, there is no way that I'm getting the same thing. No, because I'm not getting a number nearly big enough. So unfortunately didn't yield a perfect number every time. So he then noticed that if this bit itself was a prime number, then you get a perfect number. So this bit in here has to be a prime number. And because 2 to the 11 minus 1, as we saw back here, is not prime, that's why it doesn't generate a perfect number. So if 2 to the 13 minus 1 is prime, then this formula should generate a perfect number. Anyway, that's just a little aside. And these ones that are called, these 2 to the p minus 1, are in fact a category of primes known as the Mersenne primes. And I'm not sure if it's just because he worked on it, because obviously Euclid had already come up with this set of primes. Mersenne obviously spent a lot of time examining it, I imagine, in the 17th century. So he was looking for these particular prime numbers of this form, which are unbelievably rare apparently. So that's just a little bit of a side and some history. Here are the first few of those. So these are the ones, the 2 to the p minus 1, and the values of them. And there are only 47 of them known, which is not surprising because along with the perfect numbers, in fact there must be 48 now because I have 48 perfect numbers. And that's the largest. That's the 47th one. It's that big. Anyway, moving on. There's lots about perfect numbers. And these are the kind of additional things that you can throw in to try and get kids to see some interesting things about numbers if they're interested. And the fact that, yes, it is part of the history of the development of maths. And there's some nice things in here that you can sort of look at about them. Right. So knowing about primes leads us on to knowing about composite numbers, which are just numbers greater than 1, which have more than 2 factors. So the fundamental theorem of arithmetic, as Matt was saying, Euclid proved this, that every composite number can be written as a product of prime factors in one and only one way, which is great, because if we couldn't, we'd all be coming up with different ways to make a number, which could lead to different complications with there's probably all sorts of applications for it in terms of manufacturing and just making sense between each other. Not to mention the fact that the students would not have a surefire way to find the factors of something. So, does anyone know a method for finding the prime factors of, for example, 36? Anyone who, yeah, Mark.
Yeah, is it just a case of dividing by 2 down, and then basically just trying to, when you can't divide by 2 anymore, divide by 3, divide by, and then you do primes as you work up from there.
Yeah, absolutely. When I was a kid and we learned this, they were called factor chimneys, and we used to do them. I'm just going to change them to the. Oh, what have I done? Oh, so I remember doing these with, like, I think, yeah. So we just did it like this. Sorry, I should really get. I have got a pen that writes, but I've been lazy enough of this. That is an 8, a 1. Yeah. So you just sort of went down like this, and you got this chimney shape. So that was what we did. I haven't seen anyone do that in years. In fact, you're absolutely right. You go down doing that. But now we use factor trees more commonly. I mean, you know, you're welcome to teach these any way you like. But the core method at the moment is factor trees. Seem to crash the system. Right. Sorry about this. While it's loading, does anyone have any questions about anything that they've come across so far in the slides, or anything they've come across at school so far? I'm lost as to what's going on with it. I'm going to have to shut it down. Sorry about this. I think it's fine. Can you guys still hear me? Just trying to see if the whole thing's crashed. You can. Okay, good. I've obviously just crashed the PowerPoint by writing on it. Normally fine. Okay, when it disappears, that's just me trying to figure out what it is. What is not doing anything. Okay, I'm going to end the PowerPoint and see if I can. Okay, sorry about this. Okay, let's reopen this. Start on the next slide at the very least. Right. So yes, so now we do it as trees generally, where you sort of do lines off. So you actually write, you divide by 2, and then off the other side comes the 18, divide by 2, and 9. Come on, divide 9 by 2, so we try the next one up, which is 3, and just work your way down, you know, up through the prime numbers as you need to. You can just, you don't have to start with the 2. It's just a simpler method to explain to the kids. They are, if they want to, they can do 9 and 4, and then from that do 3, 3, 2, 2. It doesn't matter at all. Whichever way helps them. That relies on them obviously knowing their times tables, and so part of this, dividing by 2, is a kind of an easier way. However, if they struggle to do 2 into 36, well, they're going to generally be in trouble, but it could take them some time. So that means that the number 36 in terms of prime decomposition is made up of 2 times 2 times 3 times 3, and always get the students to check that that actually works. So 2 times 2 is 4, times 3 is 12, times 3, yes, they have got back to 36. And they can write it just like that, it's absolutely fine, or they can write it in powers. So this is just a word about multiples. The students find this terminology confusing in terms of a factor and a multiple. They want to call factors multiples because they're thinking they multiply and they get a bit confused with it. Whereas the multiples are what you get when you multiply them by something, really. So the multiples of 3 are when you times them by something else. So 3 times 2 is 6, 9, 12, 15, and so on. Basically the times tables. So you've got to somehow get them to think, maybe make them do something that gets them remembering it, or make posters, something that makes them think factors are small. So they're always going to be the smaller numbers which make up your number. Multiples are bigger than your number. So because you've multiplied your number by something. So it doesn't help that they're then asked to find the highest common factors and the least common multiples. And as you can imagine, their brains shut down and they just want to cry, because having to think about what that actually means, well, I wonder how many of them actually worry about what it actually means. But so the least common multiple. So the multiple is a number that's bigger. Common is one that's common to both of them, because you'll get asked a multiple of 2 numbers. The least is the smallest one of those, because if we've got 3 and 4, 3 and 4 divide into or have a common multiple of 12, 24, 36, and so on. We want the least one. We want the smallest one. So the smallest common multiple. I think there might be one thing called smallest common multiple. No, least common multiple is what it's called at the moment. So that would be 12. In terms of ways to figure that out, often the students find this way of just writing down the times tables makes the most sense to them. Hopefully, if they develop a stronger number sense, that wouldn't be required so much, and that they can hopefully kind of jump up through it themselves. But, you know, there's never anything wrong with writing stuff down and actually encouraging them to write down their mental processes right from the get-go is really important, because although these things become very easy and able to do them in their head, should they make a mistake, they've got no evidence for it. So again, it's just getting them to write everything, no matter how tedious. The only thing I would say is if their tables are really lacking, and it takes them an absolute age to do this, unfortunately, it is getting to the point where you've just got to say to them, right, we're going to spend quite a lot of time just doing tables tests. If you find that a large percentage of your class do not know their tables, it is totally worth going back and saying, right, we're learning this by rote. We're going to have sticker charts and treat you like children if necessary, but this is so fundamental, and it's one of those things that when I started, I was like, oh, wow, there's the old kid that doesn't know their times tables. Okay, right, well, sure, we'll get around that. And those kids, they fail, unfortunately, because everything is built on knowing those tables. They just can't get through the exams quick enough if they don't know them. They find they're having to do everything by addition. So to write out these, they would have to go 3 plus 3 plus 3 plus 3, which is all very well with 3s. But when they're counting everything on their fingers to get their 8 times tables and so on, It's getting very tedious. And it affects everything. It means that when they're trying to do division, they don't know what numbers they're looking for, and when they're trying to do fractions, they can't find a common denominator, and the common multiple is effectively the same thing. The first thing, obviously, that they can think about is 3 times 4 is 12. So you know that is definitely a multiple. But the question is that the least common multiple? So it's often worth starting from the 3 times 4 and coming back from that, saying, is there anything smaller before that? Because we know that anything bigger than that, we don't need to know. Yes. So to find the lowest common multiple of 2 numbers, we've got 36 and 56. The first thing you need to do is to do the factor trees. So they do their factor trees in order to write down, sorry, this is an alternative method, I suppose, rather than going up through the times tables. This is a method for those that don't like things and don't know the times tables, I suppose. Often the GCSE questions lead them in this thing because they've actually said to them, we want to know what the prime factors are. Now tell us the lowest common multiple. Now tell us the highest common factor. So because of Euclid's theorem of arithmetic and the fact that there is only a certain way of writing each number, that helps us to find the lowest common multiple. Oh, the lowest common multiple, yeah, least common multiple. So we've already done 36. We know that's 2 times 2 times 3 times 3. 56 is 2 times 2 times 2 times 7. So, from that, does anyone know how to find the least common multiple, the lowest common multiple? Sam?
We've just, funny enough, just done it this week. We've been using the Venn diagram.
Oh yes, yeah, I was going to get to that, yeah.
Yeah, I've been using that method to find it.
Yeah. So had you, before you'd done this at school recently, had you seen this before?
Yeah.
Right.
I've done this before, yeah. But yeah, definitely this week they've been using Venn diagrams for it.
Yeah, and I would say that's a really great way to do it. I only came across that recently, the Venn diagram, well, you know, in the last few years, the Venn diagram method. So we will skip along to that because the lowest common multiple is all about looking at what do these two have in common in terms of their factors, and then what's extra. So we write down all the 3 that we've got here, and then we look at the second one, and we've already taken 2 2s. We need to write down another 2 and another 7. And then when we multiply all of that together, that gives us our lowest common multiple. Okay. The lowest common multiple is in fact 504. If we just multiply those together, aside from being incredibly tedious and quite difficult long multiplication for a lot of the students, it would not give us the lowest common multiple, just a multiple of them, because we'd be repeating these 2 2s, which aren't necessary because they are common to them. I was just talking about highest common factor because we need to do that before we get to the Venn diagram. If we think about the prime factors of 24 and 30, 2 times 2 times 3 is 24. 2 times 3 times 5 is 30. The factors they have in common are a 2 and a 3. So if we multiply those 2 that they have in common together, we get the highest common factor. So the highest common factor is the largest number that will divide into both of them. I often find with 24 and 30, you get a lot of kids looking at them and going, 12, okay, just writing it down. Not really thinking about the fact that 12 is not to go into 30. Just one of those weird ones that happen. Whereas if they write it out as the prime factors, they can then see what prime factors do they have in common, because that is the highest common factor. So they've got 2 and 3, so the highest common factor is 6. And as we can see, 6 is the biggest number that can go to both of them. So if you ask to find highest common factor of 2 larger things, again you find the prime factors and look at what they have in common. So 120 is 2, 2, 2, 3, 5. 180 is 2, 2, 3, 3, 5. So they've got 2 2s in common, 1 3 in common, and 1 5 in common. So the highest common factor will be 2 times 2 times 3 times 5, which is 60. There we go. So, as Sam was saying, as a Venn diagram, this is the 24 and the 30, this one. You write out the prime factors that we had. So 24 is 2, 2, 2 and 3. 30 is 2, 3 and 5. So they have a 2 and a 3 in common. So the ones they have in common go in the overlap, and the ones they don't have in common go in the outer circle. The outer bit of the circle. So the overlap is the highest common factor. 2 times 3 is 6. And if you do all of the bits, all of the numbers times together, 2 times 2 times 2 times 3 times 5, you get the lowest common multiple. So it's really nice and clear because the students don't have these two repeated. So they're not going to get a multiple that is not the lowest one. But has everyone seen this, or who hasn't seen this? Does it make sense, Mark?
Yeah, it makes sense actually. To be fair, it's to be honest, it is just like when we're writing out the common multiples, but using circles to cover the ones that match. So
yeah, and I think because it's got a nice sort of visual representation, hopefully the kids are less likely to make mistakes, that it appeals to sort of different learning styles. So what I want you to do quickly is you guys have a go at doing the same 36 and 45. So you're going to have a go at using this Venn diagram method to find the highest common factor and lowest common multiple of 36. So put your hand up when you find the highest common factor and the lowest common multiple. Sam, what did you get?
Highest common factor I've got is 9. I've got 9 and 180.
Yeah. And when they taught this, how did they do it in order to did they teach each bit separately and then show the Venn diagram? or have they got...
They started off with it was working out, changing lesson times in minutes and working out what combinations they could use throughout a school day. Worked out the little tree diagram.
Mm-hmm.
She explained that they'd obviously done Venn diagrams in the previous lesson.
Oh, right.
Introduced it that way.
Right, I see. Oh, that's quite nice. Okay, so that led in from a lesson of Venn diagrams. That's quite good. And the real life application. Nice. Okay, thank you. Right. Moving on very briefly, I put this in the slides that we had that we didn't cover in the intensive study week. So if we have a recurring decimal, such as 3/11, that repeats and repeats and repeats, 27, 27, 27, 27. So we have that has a cycle of length 2, or we call it the period of length 2. That's how long it's how many digits it's got before it repeats again. Hopefully you have a calculator. If you have a calculator and you do 1 divided by 17, bizarrely mine is incorrect, so it's not showing me all the digits. That's very helpful. Decimals, sorry, I'm just keeping this folder. I'm guessing because I've got all fractions. Sorry about you, but I'm not getting anything sort of recurring on either 170 or 190. If you do 1/11, I like 2/11s, or in fact 1/3, let's go back to the simple one. 1/3 is 0.3 recurring. I see that I've got my digits set very low on my calculator, so it only gives me a certain number of them. So you'd want to be able to see more. But what I was going to look at today is how do you convert a recurring decimal into a fraction? Does anyone know? Matt?
I was always taught to sort of turn it into an algebraic equation.
Yeah.
So say I had 0.7777 recurring.
Yeah.
So you turn that into x, times both sides by 10x equals 7.7 recurring, minus x from each side, so that would be 9x equals 7, 9x equals 7, and then divide each side by 9, so you get x, 7/9, x equals 7/9.
Good, excellent. Yeah, so what Matt was saying, I can try to put it on the right screen. Sorry, I've got two screens open and it's not letting me get on the top one. Right. So this is at the very top of GCSE. So the students are expected to know it in such a tiny topic, it just gets lost sometimes at the end of things. But really this is our lead into algebra, because if we've got 0.777, I've got a special thing that I can write on with a pen. But for some bizarre reason, it's only letting me write on my bottom screen and doesn't seem to connect to the other one. I don't know why, because it works pretty well last week's webinar. Use a mouse. So, if our original should just choose it not have them. So yes, if we let x be our recurring decimal, we are wanting to know, okay, how do I write a recurring decimal as a fraction? Oh, because here's the main thing that I should have said, is that any recurring decimal can be written as a fraction. So what we do is because there's only one, the cycle length of 1, like this, we multiply the x by 10, and that just brings it to 7.7 and so on. And the great thing about that little trick is it means that if I do 10x minus x, so I get on this side I get 9x, on this side I get 7.777 minus 0.777. Basically gets rid of the extra bit, so I'm left with just the 7. And that's our x, our original fraction. When we rearrange that, must just be 7/9. So we know that 0.777 is equivalent to 7/9. This one, for example, 0.272727, if that's my x, I need to multiply my x by 100 because I've got a cycle of length 2. And that will then give me 27.272727. If I don't do that, I'm only going to get 2.7272. And if this is my x, I'm not going to get rid of that stuff. So I now take my x away. That leaves me with 27. So x must be 27 over 99, and 9 divided into both those, giving 3/11 as we have it. That's just a nice little nifty technique. So, moving on, unless there's any questions. Okay. The new GCSE, which is what you're teaching from now on, has only a little bit of extra things versus the original one. So, solving problems involving direct and inverse proportion, including graphical and algebraic representations, that was always there. Understand that x is inversely proportional to y is equivalent to x is proportional to 1 over y. We're going to talk about this in a second. Construct and interpret equations, where you always have to be able to do this. The reason that's in bold is just because it's considered sort of slightly more complex. Interpret gradients, straight lines, graphs as rate of change. Recognize that graphs, recognize and interpret graphs that illustrate direct and inverse proportion. Interpret the gradient at a point on a curve as the instantaneous rate of change. So that's talking about what we'll do next year in terms of calculus, but it's basically saying at a point on a curve, if I find the gradient at that point, it's telling me, well, the instantaneous, so the rate of change just at that point. So what they can do is you can draw a tangent to the curve, or a chord is slightly less precise, and find the gradient of that straight line in order to find roughly an approximation for the gradient at the point of the curve. That's sort of preparing them for doing differentiation in at AS level, but they really wouldn't have much concept of that at this level. And then set up solve and interpret answers to do the growth and decay, including compound interest, which is one of the things that is considered quite difficult. I'm surprised that's not involved. Work with general iterative processes. That's just a general iterative process, often like sequences and series. What's the next one? What's the next one? You're just adding on something and what times is something. So when we were at the intensive study week, we were looking at direct proportion. So we were looking at wages being directly proportionate to hours, which means that we could write that as some sort of equation that the hours times basically your hourly rate gives you the wages. We were then able to use information that we were given to find what the constant of proportionality was. And then you basically end up with an equation which you can then use to calculate any wages given out. So we're now going to look at other direct proportion and inverse proportion. So you might be told, and they have to read the questions really carefully, not just assume that it's just a regular direct proportion. So the cost of a table doesn't have to be really, apart from the fact that that helps because it's directly proportional to the square of its width. So this is when things are directly proportional to the square of something. They've told us that a 10 centimetre wide table is £200. So that's the information that we're going to use a bit later. Because it's given, the students kind of immediately jump on the numbers and want to do something with the numbers right away. But unfortunately, they've got to come up with the initial thinking. They've got to interpret what this means into some sort of math language. So if I call the cost of the square table C and its width W, what we're saying is the cost is directly proportional to the width squared. That's what this is saying. And thus, based on what we did before, we can therefore write this as a form of some sort of equation that C equals some constant of proportionality times multiplied by the width squared. Now that we've got that, we can use the numbers that they've been given, and we put that in. This is where, again, they start to make a mistake if we get the square there. 200 equals k times 10 squared, so 200 is 100k, so k must be 2. You can then rewrite this, especially if it's asked for the formula, they must then rewrite it. They can't just leave it there. They need to write, so C equals 2w squared. Often they're then asked to find something else anyway, so they'll need to then put it in there. But often students get to the end of something and think, okay, I finished, I found k, and forget that the reason for finding k was so that they could write down the equation. So what I want you to do now is, again, you are given a, oh actually, let me just do it. To show you this. This is me just doing the next bit. As I said, they're often asked to find the next bit. So they're asked to find the cost of the square table, which is 18 centimetres wide, and the width going back the other way. So they know that C is 2w squared. So if w is 18, all they have to do is sub that in to find the cost, which is 648. They find it trickier the other way because who doesn't? Multiplication is generally easier than division, and thus they get confused about where they're writing this. They've just got to think I've got costs, so that's my C. So if I want w squared, I've got to divide by 2 first, and then I've got to square root that. And they should think to themselves, okay, yeah, that makes sense, 21. Based on what the 18 centimetre was, that makes sense, so some sense of scale. So based on that, have a go at doing these. I don't know what you want to do all of them, but see how far you get through them. Is there any questions about how to do what we just did? Nothing? Well, have a go at doing these ones then. So we'll start with the first person to reach the end. So put your hand up when you reach the end. Right, you. Lead us through the first one then, Hugh. Or give us the answer rather.
Right, so the first one, f is proportional to m squared, so therefore it's got to be f proportional to km squared. We know that f is 40 and m is 2.
Mm-hmm.
So 40 equals k times 4, therefore k has got to be 10.
Yeah.
So find f when m is 5. 10 times 5 squared equals f, which is 250, and b, we've got the answer 250, so we know it's going to be 5.
Yeah, it's a bit similar to, isn't it? So should have made it a bit more complicated. So, good. Okay. Does everyone agree? Yep. Sam?
Yeah. Yes, agree.
Good. Do you want to do the second one?
Okie dokie. Do you want me to go through the work and I'll give you the answer?
You can just do the answers if you want.
I've got P equals 64 and Q equals 10.
Okay. And Matt, what did we get for the last one?
I've got R equals 150 and T equals 2.
Does everyone agree? Or agree when you get there? Either way. Okay, so hopefully that makes sense. I've been trying to get the pen to work. I have no idea why, but it's trapped on my other screen. So I can just get it to work. So effectively it's the same thing with cubed. The only difference is that the original equation when you do it is going to be kq cubed. Oh, kx cubed, let's say. So have a quick go at doing these ones. So I'll just go down myself for these and you can say whether I've done it completely incorrectly because I've just done it roughly without writing anything down. I got 25.6 and 125 for the first one. You, if I did that completely wrong.
Yeah, same.
Oh, you did, so good. And then 1080 and 9.6. Oh, let's see. Oh, okay. Well, not to worry. That's why I haven't put the answers on there so that you can do it. That makes sense. Are you all right with it, Mark? Is there anything that you'd like me to go over with these? Maybe just a case of...
No, I was alright with the process. It's just that I miswrote it when I first started and started doing it squared again, and then realised halfway through that I ballsed it up and then had to start again. So the process is okay. They'll just copy math up.
Great, that's fine. And but you know, the kids will do exactly the same, especially if you give them a load of questions where they're all modelled in together. So it really is a good way to get them, to force them to read questions really carefully and then check that what they've written is correct based on the question. I mean, so frequently when I'm marking, so much of it is just miscooking, which is a right pain because you can be a little bit kind and give them a few marks, but not many. Now, same thing again. It's just to root x now. So if it's directly proportional to the root of x, you're just saying y equals k times the root of x. So have a go at doing these ones as well. Oh no, sorry. Ah, okay. Sorry, I was trying to fiddle with the pen again, and I see that I have now managed to do that. I've also annoyingly put my webcam on here. It put me off, so I can't see myself. Now I see what I've done. In order to get my pen thingy to work, I've had to sacrifice my other screen, annoyingly. Which means that I can't see you. Let me just take you guys over here. This is what it looks like to me. I don't know what it looks like to you. Yes, I can see you over there. Common errors with this one is just forgetting to square root at the end, for example. So I think we end up that y. Oh, no, hang on. So we end up that y is 3 root x. So when x is 81, that's fine. We've got 3 times the root of 81, which is 3 nines. It's the other way around, really. When y is 147, and actually every time get them to write out the original equation, make sure they don't forget that. That will avoid a lot of issues going forward. So 147 divided by 3 is 49, is root x. So what is x?
I got two. Do you want me to say it? Sorry.
Yeah, go ahead.
Well, I got 2,401, which is the square of 49.
Yeah.
At first, I can see why it's confusing because 49, obviously, if you square root that, it's going to be 7. So I can see where kids might go wrong on an exam and just square it.
Yeah, it was deliberately mean. Because it's a square number, you find yourself automatically going, great, x is 7. And they might be mean like that. They might give you a number that makes you think something else. So it's just very, well, hopefully clearer there that in order to get x, you need to square the 49, which, as you said, is 2,400. Oh, I've gone off the side of the screen. Sorry, I can't seem to write anymore. Let's see this one. So yeah, that was just a really mean one. But again, hopefully, if you can get the students to then look back and think, okay, look at your original ones that you had. You had 36 and 144. So generally, well, so always, x should be bigger. So if y is 147 and you then get x is 7, that's weird. So it's that sort of thing where you kind of want them to start applying some sort of common sense. But you have to point it out initially, just to get them in that frame of mind. So moving on to, let's see if I get my screen back now. How on earth I get back right screen? No. Let's get a point back in it. I'm not sure why I hate switching, but anyway. Stop. Yes, I want to show that screen. Okay, do you know what I'm going to do? I'm just going to simply unplug that and hopefully it comes back. No, there we are. Never mind. Right, inverse proportion. So all the ones you've been talking about before, as one thing increases, the other increases. And that's why, when I was talking about this should always be bigger, that is definitely the case because it is directly proportional to it. If it's inverse proportion, then as one increases, the other decreases. So for example, as the temperature in the summer increases, the sale of gloves decreases, for example. So those two things would be inversely proportionate. Or something that makes much more sense, as the more people you get to build things, the less time it takes. So if it takes 4 people 10 days to build a brick wall, how many days will it take 20 people? So, yeah, so more people employed. So the time taken is inversely proportional to the number of people. So, for inversely proportional, we say that it's 1 over the number of people. So we don't have a different sign for inverse proportional, we just say it's proportional to the inverse. So this is where sort of our English and our maths get confused, because inverse is basically doing this, 1 over it. So we want proportional to the inverse of the number of people. And that means that we're still multiplying by a factor. It's just that it's k times 1 over p, which gives us our k over p. So we had that it took 4 people 10 days. So the time is 10, the people is 4. So to work out k, we just multiply it by 4, so k is 40. So our equation is simply t is 40 over p, and we can use that to work out how long it will take with 20 people. So with 20 people, 40 over 20 is 2, and it's just going to take us 2 days. Now, in a common sense fashion, we know that actually they reach the point where there's kind of too many cooks for the broth, or the sort of, there's a limit at which you can excuse me, increase people and for it actually to make a difference. But they don't tend to worry about that too much with the kids. So if you have a go at these questions, it's really just the same as happened before, it's just that you're now doing 1 over x. try to figure out how to get back on screen. Sorry for playing around with it, but I'm just trying to find how to look at so that I'm going to get my other screen back so that I can keep everything else on screen. There we go. So you just want to go down, well, I say alphabetically actually, no, it's not alphabetically, you're in the order that you listed the right, or reverse order in which you right. So Hugh, what did you get for the first one?
First one I got M as 18 and R as 12.
Yeah. Mark, what have you got for the second one?
Never got that far, had a complete blonde moment and got lost and confused, so never even got started.
No, so if that is the case, then just say, and then we can go back over anything you want.
Right, yeah, I figured out what I'd done wrong, or where I was going wrong right at the last, and then you started asking for answers by the time I even figured out what I was supposed to be doing. I'd done something really daft, like I was trying to, when I on the first one, I got like M is directly proportional to K, sorry, M equals K over R, so therefore 9 equals K over 4, and then I was trying to divide 9 by 4 to get K, because I did my algebra wrong, should be 9 times 4 to get K, and that's why I got myself all fluffed up. But I didn't think it looked right, so I went on to the second one.
Yeah.
and then when that didn't look like as well, and that's when I realised what I'd done wrong, and then I was just starting to work out again when we stopped. So.
Yes, well, I'm not trying to rush you. I would just sharing these things is great because all you're doing is falling into the traps that the students do, and they'll do exactly the same. And I've just been working through these in my head, and I've been doing the same thing because I didn't write it down. I was just like, what? 4 9? Why would I come up with that? Oh no, wait, I want to multiply it. So the kids will do exactly the same. So the fact that you are doing similar things means that you will then understand that they're going to fall into the same traps, and thus you'll be looking out. And when I go down marking, I know that there's kind of I'll expect to see some answers where they've got K as 36 and some answers where they've got like 4 9s and all sorts of things. So again, it's just a case of making sure that the students don't feel that they're idiots because they're not. They just simply have to really think carefully at each stage about what this means. So this is the unknown. Something divided by 4 is 9. Well, that must be 36 divided by 4. So if I get maths and science to the other two, so just so that you can check your answers. Matt, what did you get for 2?
I got T equals 5.6 and M equals 0.5.
Yep, sounds about right. Yeah, and Sam, what did you get for 3?
At 30, W is 30. And I think I've been doing it wrong the bottom half. I've divided the 90 by the 10.
Let me do it because I haven't got, because I was tapping out my screen, I haven't done it. So, inversely proportional, so 6 is K over X. Oh, let's go 50. So K is 6 times 15, which is the 90.
Yeah, K is 90.
Yeah, so W is 90x. Oops, sorry. W is 90 over X.
Yeah.
So when X is 3, it's 30, and X when W is 10. Oh, yes. So actually we should talk about this because the students get really confused at this point about how to rearrange because effectively you multiply up so that you've got 10x is 90 and then divide by the 10 so that x is 9. Let me just go back then and check with what Matt said here because I just assumed it would be right. So 7 is K over 4, so K is 28, so T is 28 over N. So if we just check that. So 28 divided by 5 is T, that's fine. And then 28 over 56, yep, is a half. Yeah, so that's where you just got to be careful. Oh, goodness me. You've got to rearrange that. So the M is 28 over 56. This is something that you do after you've done rearranging equations, really. And rearranging formulae, which is something the students really struggle with. As we were talking about in the study week, just the case of knowing what's happened and doing the inverse, doing the reverse bit. So if you've divided, you need to multiply. They find that really tricky. And because a lot of them do the same to both sides, it can get quite complicated when you've got a formula. So I can never remember the formula for Fahrenheit to centigrade. I don't know if anyone else can, but I'm going to make it up. unless anyone says otherwise. No, that's not going to be right. So it must be about something like 3, 6. Oh, what's that? I can't remember what it is. And since I do everything in centigrade, my mother and I just don't understand each other when we talk about temperature. That's it. So this formula, whatever it is supposed to be, is something that the students really struggle with in terms of rearranging, because it's got this fraction at the front. So they go, okay, so I need to get rid of the fraction at the front first. So let's divide by it. So they kind of do this and end up with this like mega fraction that they're not really sure how to deal with. It is something like 5/9 actually. Anyway, it doesn't matter. I've now changed this. Look, my miscopying is over to 5. So easy. So it's this sort of thing, and as you can see how all of this is linking together. They struggle with this because they're not very good at rearranging stuff. They struggle with rearranging stuff because they're not very good at fractions. They're not very good at fractions because they can't do their tables. And they can't do their tables because they didn't learn it by rote when they were in primary school. Anyway, so tackling these sort of things, getting them to say each time, what does that mean? This is making a fraction is dividing, isn't it? So f divided by 2/5. If you divide by a fraction, you flip the second guy and multiply. So flip the second fraction, multiply. So that's the same as saying I've got 5f over 2 or 5 over 2f. Let's see this 32, and then I'm adding 32 here, so I'm going to need to take away 32. So you could spend a whole lesson, and I don't know if we actually, I'm taking my 32. I don't know if we actually ever bothered doing this, but literally take it really back to basics and just say to them, right, I've got something f plus 3. What's the opposite? Right, so they'll just be like, this is so tedious, but it's amazing how difficult they find it. So just to complicate matters, you don't just have proportional and inversely proportional terms. You also have x to whatever, x squared, x cubed, root x, and so on. So this is kind of these are the most difficult that they would be as GCSE 4, or generally obviously proportional. So inversely proportional to m squared and inversely proportional to root q. So just take it step by step, write it out. I will do the same, and I would like to do it slowly. So you have a go at doing this while I'm writing. So I've done like a full working. I've dumped a few things, like I've just squared those in my head. But this is kind of how you'd like the students to write out every step. So there are no room for mistake. As I was doing this, I thought, oh, there we go, I've reached the end. And then when I checked it, I realised, no, that's squared, so I want m, and that's going to be really easy to trap the ball into. Which I'll do a little bit less. So. No, I should have jumped to it. I just wanted to take the way I've done that. Just go this for a loop. So, that's not very nice. This, where it's inverted portrait to a root, definitely. The root ones are definitely the trickiest, aren't they, to think about. To not square or root in the wrong, back to front. I didn't like it. Does anyone disagree with it and have any questions about it? Okay, well, I think you're probably a bit brain-tied. There's some extra things there. What we'll do before kinematics is, and I'll leave this on here, is have a quick break. Okay, so if we have 5 minutes just to go and get a cup of tea, well 5 or 10 minutes. Should we say 10 minutes? So 11:05, have a cup of tea or coffee, and then we will do kinematics, which is the rest of what we've got. Is there any questions about what we've done so far? Okay, Matt, yes. Is that you asking a question? I can't hear you.
Oh, can you hear me?
Yes, I can now. Yeah. Can't hear you now though if you're asking a question.
The subject development audit.
Yes.
I completely lost a piece of paper with your alternative email, so I sent it to your Brighton one.
I have got it, thank you. Yes, I
oh, that's great.
And I don't know if I gave you another one actually. Did I give you my other email? Hold on. I check the Brighton one regularly.
Oh, I think it was another lecturer who said they don't check their Brighton one very often and gave us a different email address. I think. Yeah, great. As long as you've got it.
I have, thank you. I've got everyone apart from Hugh. So Hugh, please do your subject audit. The sheet is on Student Central, and fill it in and send it to him, and I can see, where you've got issues. The stats, just sort of as a general thing, looking at the ones I've had so far, stats is a common issue, because unless you've gone into a statistics role, you don't use it very much. And there's a lot of data handling stuff that I don't know if people didn't do it at school, or whether it's just one of those things that you easily forget. No, I think something we just didn't do. It wasn't such a focus, was it, when we were at school? So we will do a lot of stats, because it does seem to be quite a lot of the GCSE now. And we will gradually cover things so that hopefully when you look again at your subject audits at the end of the year, it will be completely different, hopefully. Anyway, I will see you at 11:05. Go and have a break, and we will talk in 10 minutes. Right, when you're back, yeah. You and Matt, are you back?
Yeah, I'm back, sorry.
Yep.
Okay, great, that's all right. Yeah. It's always this, it's such a weird thing, this. I just kind of talk into thin air and have no idea. How are you, in fact, just in terms of some feedback, how are you guys finding it? Pam?
Just fine. Yeah, no, it's fine, really. Except my dogs decide to run around the house like a lunatic.
Is you finding it weird that there's this like out of body voice talking, disembodied voice?
Well, I think with previous jobs in the past that I'm sort of used to it. Distance problem solving.
Right.
Yeah.
Yeah, and Hugh, what were you going to say?
No, just getting on with it fine. It's just a bit difficult, sort of with the small space I've got just now to work with.
Right. Matt, what were you going to say?
Oh, sorry. Yeah, no, it's going fine. It's I feel less brain fried than I did on the intensive study week, so that's good.
Yeah, sorry about that. The clue is in the name with the intensive, but I think perhaps I broke you guys a little bit, and sorry about that. The pace with both is very difficult because, of course, there is so much that I could tell you about. And this year we won't even cover every little thing from the GCSE. There's sort of, picked the major things out of it. And the webinar pace, this is why we record it though, so that you can go back and look over it. And all of the resources and the PowerPoints are on Student Central. One thing I was supposed to do when I made the announcement and sent you the email about registering for the webinar is I'm supposed to put a link which takes you to Student Central so that you don't have to hunt through study materials. And I'm sorry I didn't do that, but I can do that in future. So the final thing that we're going to talk about today is kinematics, which is the study of motion, is actually what kinematics means. And this is, part of this is new to GCSE. It wasn't kind of separated off so much as a separate thing. But it leads on, as we were saying before, about formulae. So substitute numerical values into formulae and expressions. So it comes towards the end of algebra when they're able to substitute in and rearrange things. Plot and interpret graphs, including reciprocal graphs and exponential graphs. Whether they know this terminology, I'm not sure. Yeah, they should know the word reciprocal. I remember seeing a GCSE question actually which said write down the reciprocal of this, so they should know that terminology. Anyway, part of the plot and interpret graphs includes problems such as simple kinematic problems involving distance, speed, and acceleration. Now, they've always had distance time graphs and things like that, but the bringing in the acceleration is a new bit. Calculate and estimating gradients of graphs. This is where we've been talking about drawing tangents to curves if it's a quadratic graph, and estimating areas under graphs, for example, by imagining that you have them as rectangles or trapezoids, something like that. And triangles, distance time graphs, velocity time graphs, and perhaps financial ones, but that's not in kinematics. So the kinematic stuff's the bit I've put into red. So it's kind of hidden amongst this stuff. So just looking at the old curriculum versus the new curriculum, they've always been doing the basic formula of speed, distance, time, and doing distance time graphs. That was already at GCSE. But what's new is that they're now including the constant acceleration equations, which I call the SUVAT equations. And they've got velocity time graphs, so not just distance time graphs. We don't know really what the questions will look like. So what I've done is I've chosen some from AdMaths that may be similar. So, distance is speed times time. Speed is distance over time, that's the two things rearranged. Have you come across this teaching the kids yet? Obviously, I haven't been there very long, but how do any of you know how the students remember these, or how you can help the students? Sam?
I did with the autistic kids I was working with. We just drew a triangle, put the D on top, and then the S and the T at the bottom.
Yeah, absolutely.
Oh, there you go.
There you go. Yeah, well done. That's exactly it. You know, there's just so many generic things that we do with good reason, because it really helps the kids. The triangles, they like the triangles. The nice thing about the kinematic one is that it's in alphabetical order, starting from the top, so they just have to do DST. So they don't have to even kind of learn the triangle, they just have to remember that there's distance, speed and time. And provided they start at the top and write it in alphabetical order, they get it. Really helps when we're thinking about units, because if you think about distance, in fact, just for anyone who doesn't understand using the triangles, they the line is basically meaning divide. So if I look at this bit and so if I cover up, sorry, I've just reached my hand up and covered up. I'm moronic. Okay, sorry. Obviously you cannot see that. But if you imagine that I've covered up the T with my hand, because I'm trying to find T, then what I'm left with, so if you reach your hand up to your screen and put it over the T, you're left with D over S. So time is distance over speed. Equally, I can put my hand over the S and cover the S up, then I'll try to find S, and I've got D and the line over the top of the T, so speed is distance over time. And then if I cover up the D, so I'm trying to find distance, I'm left along the bottom with speed, and I know it's a bit weird because it's like a vertical line, but it's basically we're multiplying by the T. So that's how the triangle works. They can cover up each bit with their hand, and then they're left with the bits they need. When I'm talking about units, if we think about what's happened, distance is measured in, for example, kilometres. Time is measured in hours. Then when you're thinking about the fact that speed is distance over time, in units terms, that's kilometre divided by hour. And that's what this means. When we write kilometres per hour, it's because it's a fraction. That's what the per means. Kilometres, 1 kilometre, or however many kilometres per hour, is saying if we want to split that up, we divide it by the number of hours. So the units linked to the division that we're doing. So speed is therefore kilometres per hour. Now, as they get to AS level, you can write it like that. This is going on a bit and it's a bit more advanced. You won't do this at GCSE, but this is just bringing us back to our indices. It's because when you divide by something, it's the same as timesing it to the -1. That is an aside. So, now I'm going to cover up my writing. What's the difference between speed and velocity? Does anyone know? Yeah, Matt?
Velocity could be, velocity is two things, it's direction and magnitude, rather speed is simply magnitude, so velocity is a vector rather than speed.
Yeah, absolutely. So we use the words, well, I suppose it's one of those things we use incorrectly in the same way that we kind of use weight versus mass incorrectly. It's the quantity versus the actual sort of quantity in a particular direction. Now, generally, when we are talking about something in these questions, more often than not, they are actually talking about the velocity. They're talking about a car going along a road, so it's in a particular direction at a certain speed, so at a certain quantity of velocity. So yes, so it could be going 60 miles an hour is just the amount, so that's the speed. The velocity is that it's going 60 miles per hour west. So yes, velocity is a vector, as exactly as you said, both direction and magnitude. Speed is simply how fast it goes, just magnitude. Thank you for your mathematics. So this is off. I think I took this from the Growth Mindset website, which did I show you that? Hopefully, I think I just she has lots of resources on there, split into categories. She's got these learning journeys so that you can get the kids to plot where they already are, and then by the lesson they can say, oh look, I've moved up to this level. Oops. So very simply, the very simple ones for sort of grade D. So John left home at 9 o'clock to cycle to Milford, 20 miles away. This is covered up, but it says the graph shows his journey. So just have a look at the graph and these questions and have a go at answering them yourselves first. Obviously you can't draw part D particularly on the screen, but you can describe it. So So Hugh, have you had a go at all of that? Can you explain to me?
Yep, sorry, I messed the button when I tried to click hand up.
Sure. So how far did John travel in the first 30 minutes?
5 miles.
Yeah. And what time did he start moving again?
09:45.
Yeah. And how can you tell that he was travelling more quickly?
If you look at the gradient in the graph from 0900 to 0930, it's quite smooth. Then from 0945 up until 1045, it's a lot steeper. So if you work out the gradient, you can show it mathematically.
Yeah. Absolutely. And what time does he get home?
1300 hours.
Yeah, thank you. In fact, if you're thinking about what the students think, and think about your processes as you were reading this, your first kind of step, I mean, I don't know about you, but my first sort of step is thinking, okay, what is this showing? Okay, this is the distance. So in the first 30 minutes, that's going to be 9:30, because you've just got to think about what's the scale here. And so at 9:30, we're at 5, so he's gone 5 miles. The students will do that in just a lot, a lot slower. They find reading scales and graphs incredibly difficult. For a lot of them, their ability to tell the time is a bit of a hindrance. Or their inability to tell the time is a bit of a hindrance. And once you do a more complicated graph than distance time graphs, so if you do move on to velocity time graphs, they often forget then the simpler ones where you've just got the distance. So they try to work out things from the graph. So they start calculating the gradient. So this is okay, 5 over 30, so just, although they might be asked, and in fact that leads me into my next bit, they might be asked to calculate the velocity, well, the speed in fact, because speed is distance over time. Technically, velocity is displacement over time. So where we were saying that velocity is basically just the vector form of speed, so it's speed in a particular direction, displacement is distance in a particular direction. So in terms of the fact that he returns home, his displacement ultimately is 0, because displacement is all about the distance from your original position. And because he's gone out to Milford and come back again, at 1300, his displacement is 0 again. However, his total distance, so what, he's done 20 miles out and then 20 miles back, so his total distance is 40 miles, which is again another question that might be asked. And calculating the gradients, because as you said, the steepness of the graph tells us how quickly they're going, because that is the speed. So, as I said, the 5 divided by the change in y over the change in x gives us the gradient. And so we can calculate that here he's going at, well, 10 miles an hour. And here he's going at 15 miles an hour. So that's faster. And he must have been speeding down a hill all the way back to get up to 20. So here we are. Here's another one. Judy drove my home to the airport, waited at the airport, and drove home again. Here's the distance time graph. So it's just getting them used to, again, time, appreciating what's going on, reading graphs, reading scales, and so I'm not going to ask you these two, but work out Judy's average speed on her journey home from the airport, giving it answers in kilometers per hour. So just have a look. I know it's quite difficult to see on the screen, but kilometers a while. So how do you work out average speed? Mark?
Yeah, so working out the average speed, you simply take the total distance as you had, divide that by the minutes that it took to take it, and multiply that up to 60. It gives you the average speed.
Yeah. So when you say multiply up to 60, I think for us, we have a sense of doing that. I don't know about you, but as I drive, I'm maybe a bit sad at doing this, I don't know. I'm always calculating, oh, I'm going this fast, so I've got this long, it's going to take this long. I sort of do that calculation repeatedly. And we often do that because we are, as adults, more used to doing these sort of things. And the kids, to them, this is just maths. And so some of them will be able to do that. So what is it? Sort of just travel back 40 kilometres in half an hour. So we know, okay, right away, half an hour is, as it says, half an hour. So we can just double it. That sense of just double it to get an hour, they might not get. So you'll find them doing 60 divided by 30 equals 2 times that. So then they're not thinking about it as, they're just not really thinking about it. They are just applying a numerical method, which is fine in itself, provided they can do it, but it's nice to get them to think about it as well. So moving on to the acceleration question. So this is the new bit. They are being given these formulae though. At AS level, when we're looking at mechanics, that's our very last webinar that we will ever have at the very other end. At AS level mechanics, they have to know these off by heart. But in the new GCSE, they are being given these formulae in the exam. So they just need to know how to use them or what the letters stand for. Easier said than done. The formula sheet that is given at the beginning of the GCSE is completely useless to many, many students because they think to themselves, oh, I don't have to learn that because I've got the formula for it, but actually have no idea how to use it. And for years, going forward, they're not being given this, but for years they were given the quadratic formula, for example, which we will look at the next webinar. And they really, marking it, you just be like, what on earth? You're given the formula for this, and yet you have just written it completely incorrectly. How can you get so far away from what's correct? And it's just a lot of them thinking that they know it and getting, and a lot of them just not understanding which bit's which with the letters and the numbers and the signs and all sorts. So, if we're thinking about accelerating, that means that initially we're going at one speed, we've got faster or slower, it's deceleration, or bit of acceleration, and so we've ended up at a different speed. Now I'm using the word speed, but we are talking about velocity because acceleration is, again, change in velocity. So in fact, it's change in velocity over time, and it's a vector as well. So we're talking about velocity, and ultimately we're talking about displacement because all of these are vectors. So this one, the v equals u plus at, is final velocity, is the initial velocity plus the acceleration times time. The s is displacement. So I think the students think that's a bit weird, they don't have to use a d, but it is an s. So s equals ut plus a half at squared. That one seems to stick. They always seem to remember that one when we do the as. And then v squared equals u squared plus 2as. There are also two other equations, but they can be formed from these, so they're not strictly necessary to know. Now, using these are typical additional maths questions. Additional maths comes in between GCSE and AS, effectively. It's often done by year 11s who have already done the GCSE early. And it's a very sort of traditional, it's very like the old A-level. It goes into about halfway into AS, really. So a car moves from rest. The car moves from rest with constant acceleration. Now at GCSE, it's always going to have constant acceleration because they haven't, anything non-constant is too complicated. On a straight road, when the car passes a point A, it's travelling at 10 meters per second. Now it won't be written like this because I've taken this from additional maths. This is what I was saying before. That's just another way of writing meters per second. So ms to the minus 1. When it passes a point further along the road, it's travelling at 16. So I've got this little point A, and at A I'm going at 10 meters per second. I go further along, and D I'm going at 16 per second, and it's taken us 10 seconds to get from A. So we want to find the distance AB. Now, the reason I called them the Suvat equations is because, I don't know why I'm doing this way, because I normally write it down. I always do that here. Suvat. That's each of the letters. That's why it's called the Suvat equations. So if we write out what we've got, we want the distance AB. So that's what we want. So if we put a question mark there, I'm just going to scribble that out. That's what we want. We've got U. U is our initial velocity. Our initial velocity is 10 because we're trying to find from A to B. It did say from rest, but it's not asked us about from the starting point, it's asked us from A. V is our final velocity, so that's 16. A, we're not concerned, we don't have, and we're not asked it to the next bit. T, we're told is 10. So we look at what we've got, which is S, U, V, and T. So if I go back to these equations here, at this stage, they've just got the formulae. At AS, we tell them to write them out repeatedly. So we've got, what have we got? S, U, V, T. We're looking for ones that have got S, U, V, and T. In this case, we are going to have to use two of them anyway. So we may as well calculate the acceleration first because we're going to have to use that to get the distance anyway. So if we actually do the second part of the question first, we can use V equals U plus AT. But it's that ability to check what they've got and check it against these and see what they've got. So they're like, oh, I've got V, I've got U, and I've got T, so I could use that one to find A. And then when I've got that, I'll go and have all of these ones here. I'll be able to find S. Or equally, you'll have all of those ones, but it's not very nice because I'll have to rearrange that. So it makes sense to always use the one that's easiest. So V equals U plus AT. So 10, I'm sorry, V is 16. 16 is 10 plus 10t. Rearranging, 16 minus 10 is 6, divided by 10. So t is 6/10, which is 3. Sorry, Let me do it again. There we go. A is 3/5. So A is 0.6 meters. What units, in fact, is acceleration measured in? Matt?
Is it meters per second meters per second per second?
Yeah, exactly. So you're right. I think we tend to, well, it's difficult to know at GCSE because we haven't really used this before, but meters per second squared, or meters per second per second. And the reason for that is if we think about what we're saying acceleration is the change in velocity, because actually if I just change this around, which I could have done as well, I could do v minus u over t. So that is the change in velocity over time. That's what acceleration is. So velocity is measured in meters per second. So we're thinking about units again, and it's over time, so it's per second. So it's meters per second per second, or we could call that meters per second squared. So again, the units, I don't think they come down on them very hard in GCSE about the units, but you know, they should know. So we found the constant acceleration, so we can now put that into S equals a ut plus half at squared to calculate our displacement, our distance. In fact, they've said distance. In this case, because it's travelling all in the same direction, it will be distance. And at GCSE, they would only have things happening in the same direction. I don't think they'd have it driving somewhere and coming back so that you ended up with a displacement that was smaller than the actual distance. So again, it's just about substituting in our values. So we've got ut, so u is 10, t is 10, so we've got 100 plus half at squared, t is 10 again, so half, so 50 times 0.6 is 30. So, did I do that right? Yeah. So a distance of 130 meters. Are there any questions about that? I imagine for some of you this is something that you'll be using all the time. Mark?
Yeah, I must admit I looked at that and I got a little bit of I kind of follow it, but it's, yeah, I wouldn't mind seeing it a couple more times and I'll probably have it done then. But yeah, it's a little bit.
So would you prefer to work through this one? Would you prefer me to work through this one, or would you prefer to work through this one?
Yeah, I mean, I wouldn't mind having a crack at it. I'll just sort of flick up that thing, get those formulas back up again.
Yeah, okay, I will show you the formulae. Hang on, this is not going to work. How am I going to do this? I'll write the formulae down here again. Okay.
Okay.
If you guys have a go at this second one, I will write the formulae. But it's worth just underlining what it is that you've got, and writing out the SUVATs, you know, what you've got of each bit, and then you can decide.
Sarah, for the first question of the distance AB, I used the equation S equals U plus V over 2 times T.
Yes, that's one of the other ones.
Came
Absolutely.
Up with 30. Is that just because we didn't have A, and if I got A wrong, then it would muck up your first answer? So.
Do you know, absolutely. And that at AS level, I expect them to learn all 5 of them and to use the ones. So I always say you don't know A, so if you muck it up, you should always use the ones they've given you. You're absolutely right. And it was just unfortunate because they're not given that at GCSE. They're only given these 3 in the formulae. But yeah, absolutely. I would normally say, ooh, I would avoid using, and generally, wherever possible, avoid using the ones that you've had to calculate, because with that exact same reason, you could knock it out. So yeah, that's no problem.
So if there are sort of a high ability GCSE group, would you encourage them to learn the other 5 equations just to check their answers in questions like this?
Yeah, well, they'd only need to learn 2, wouldn't they? Because they've given
I suppose so, yeah.
So I think so, especially if they are, keen physicists, they might come across it anyway. And keen physicists, I don't know if those people exist very much. Oh, sorry, I didn't mean to. I didn't mean to press that actually. But yes, I've got a nice sheet actually where they kind of discover each of these by using the graphs and calculating areas under graphs, using trapeziums and things like that. And they derive each of these. And then by simply substituting in the other bits, you can get what you require, because yes, you could sub that bit into there and get out the other equations. So yeah, it's worth doing with the top set probably. And saying to them, do you see that avoids doing that? But then it doesn't matter either way, does it? Because in the exam, if they forgot, they've still got these 3 formulae. I'll start all this stuff over slowly. Right. At what point, Mark, did I lose you?
Right. Yeah, I decided to go with the third form with their v squared equals u squared plus 2as.
Mm-hmm.
So I started substituting in some of the known values. So I ended up with 6 squared equals 90 squared plus 2a times 21/6. Put up the squares. So I got as far as 36 equals 8100 plus 2a 2016. And to be quite honest with you, I just couldn't figure out where to go from there.
Yeah, and that's the same. So this level of algebraic manipulation is right at the top end of GCSE. The students also struggle to figure out what's going on. And it's basically, you've got to think to yourself, okay, I've got a number plus something that's being multiplied. So if I wrote, this, and I'm trying to find the x, what's the first thing I need to do?
Or would you take would you do? No, you wouldn't do that, yeah. I'd take 3 from the 5.
Exactly. And that's exactly the same as this.
Okay.
It just,
Okay.
so you've got to, this is, you know, we were talking about like the equation machine. You have to think what's happened. So x has been multiplied by 2 to get the 2x, and then it's been added 3 to get the whole thing. So to come back the other way, you've got to take 3 first, to get whatever. So this is 5, isn't it? So we take 3 to get 2, and then we divide by 2 to get 1 in this case. It's the same with this acceleration. So you've got your 36 and you've got to take the 8100. It's not nice either. When I say not nice, I'm also saying to students, what do you mean not nice? They're like, oh, it's not nice numbers. They've got a feeling of like, oh, they don't like big numbers, they don't like negative numbers, they don't like things that aren't whole numbers. So yeah, it ends up with that you've got minus 1764 on the left hand side, while you've got 4032 times a, when you times the 2 and 2016 together. And then that's like the 2x, you've then got to do the opposite, you've got to divide by 2, or in this case, divide by 4032, which seems hideous to them. Minus 1764 divided by 4032. Obviously only going to be on a calculator paper.
Yeah, I mean, I worked it down there, you end up at -2, don't you? Whatever, -2 kilometres per second, I think it is.
Oh, have I done it wrong?
I don't know. Don't take my answer as right.
Yeah, I agree with Mark. I think you.
Whoopsie.
I think there's a mistake in.
I know what it is. I took 1800. I can see that right away. Yeah, I can see that right away. I've taken 1800 instead of 8100. So I'm sorry if that led to further confusion.
I mean, until I got the arrangement of the formula, I was completely lost without even looking at what you did, so don't worry about that, that's fine.
Okay, so that should be 8064, and now I can see that would be much nicer. I thought that was a bit overly complicated. Right. And I should have thought to myself, does that make sense? I thought, oh, that's very little. Right, and this is why, as we sort of discussing that, I don't really want to use the stuff that we just used, because now I've put it up. Is that right? Well, I'm thinking to do it now. Okay, 52 seconds, 6 minus 19, 84, 2. Yeah, so apologies for that. As you can see, oh, I can't remember the word, transposition. So where I had simply looked at that as 8100, in my head, I then took away 1800. So common, so common. So yes, I should have looked at that and thought, 1,700. Anyway. So it is, as I said, the sort of, you may not get to this point at all with, if you've got sets, if you've got them set, your C and below, your D and below classes, if it is set like that, unfortunately, you may never do this with them, because substituting into formulae is hard enough. These are particularly tricky formulae. Rearranging them, it's a real struggle. And I mean, like for you, Mark, I would just say this is something that you're going to need to do lots of practice, because it's going to be one of those things that, it's a
yeah,
really
fair one. It's manipulation of some of these formulas, just with that many bits on it, it's something I haven't done an awful lot of. So
yeah, and it's just the case of that. You just need to do lots and lots of it, and you'll get the hang of it. It's just a case of being able to spot, like this that's happening up here, where I can see that's happening by looking at this. It's just getting a feel for it, that all the extra bits that are tacked on, you've got to get rid of first, and just doing the opposite all the time. Yeah, the kids really struggle with it too.
I think that looking at it again, I think the bit that threw me was when it was 8100 plus a 2A 2016. If I'd put it as 2A 2016 plus 8100, it would have been glaringly obvious. I think it's just the fact that I hadn't switched that round and they're just staring at me in the face then. I think that's where I was.
Okay, so that's good. That's something to say to the kids, that, and it is an important fact. Really sad. I was actually having this discussion with my husband this morning, when we were trying to describe this to my daughter about this fact. We were talking to her about the fact that this fact is true for numbers, but it is not true for socks and shoes. You cannot put your socks on before your shoes. So it's not, and then we couldn't remember, we were having an argument about whether we call it transitivity or reflexiveness, but I think it's reflexive. The fact that adding two numbers together, it does not matter in which order you do it. So yes, if turning it round so that you've got the unknown first helps, then absolutely do that. So that might be a handy hint for them, just about how it looks, or to sort of say to themselves, okay, forget about the numbers. What does it mean when it looks like this? Because this is exactly what it is. Right. This is not to scare you. This is just to show you where we'll be getting to right at the end. This is mechanics question, which is one of the modules that they can choose to do as their applied module at AS level, because AS level has 2 core modules and 1 applied, so two pure and 1 applied. Not much difference though, really, versus at the top of GCSE. So it will be interesting to see when the GCSE papers come out next year, and it's kind of the first ones of the new stuff, what is happening. That is all the maths. So you can switch your brains off now. Coming up next, over the next half term, you've got 2 self-study tasks. I have already put them up. You're supposed, they're put in for a particular week. Obviously, if you want to do them this weekend by yourself, that's fine. Doesn't matter when you do them. But effectively, supposedly the week after next is a number self-study, and the week after that is an algebra one. They're both on Student Central now. There's different ways that we can do it. You can either type them up and email them to me, or you can just sort of email me a few things saying, I don't get this one, or I have no idea where to start with this. Or you can have a go at it yourself, and if you're happy with everything, and then that's fine, and you can just sort of say to me, okay, there were a few issues. So don't feel that you have to type up the whole thing, especially if you feel, well, I understand this completely. It's not a case often of saying, what is the answer for this? Though there are some. So if you want to know what some answers are, just ask me. but I haven't got like a solutions sheet that I've typed up that's a bit different. So have a go doing those. The next time that I speak to you is not until Friday the 13th, which is unlucky, but anyway, of November. Well, that is the unlucky bit. You're going to have a really intense webinar on quadratics. Yay! So unlucky for you, but it's hard going because there is a lot to take in. I would suggest, the stuff where we were multiplying out to brackets and stuff, try to have a practice of that. It would be going quite quickly and is the most advanced stuff. And I know this is weird, the order that we've done it in. I've continued to do it in the same order that it was done the last 2 years. I'm realising that we're doing a lot of tricky, well, it's because we start with number and algebra, basically. And in order to, the aim of these webinars and your subject course is to push you on further. So rather than doing a lot of easy stuff, obviously we are trying to do the top end of the GCSE syllabus this year. So quadratics is very much like the stuff we've been doing right at the top end of it. And again, you'll find that with the lower ability classes, you never even touch on quadratics. So this is kind of pushing you and that. And then that will be it on algebra. We will then move on to doing geometry and trigonometry. So onto sort of a different section, which is why we're sort of seemingly getting quite hard initially. So I could start, if I was to move the course around, it would be interesting to have your feedback about whether you, at the end, would say you'd prefer to start with geometry and trig or whatever. But we'll move on to geometry and trig after Christmas, or next after this quadratics one, and then we'll have statistics. So those are the three sort of big bits: the shape and space, number and algebra, and data handling. Your ongoing task, which I sort of said to you before, is that you need to try and get to grips with some sort of graphing software, Autograph or GeoGebra, or find out if they do anything in the school logo or whatever. The schools, bizarrely, despite the push on like smart boards and all of this, when I talk to people about graphing software, really doesn't seem to be greatly in use. So you might find that it is quite tricky to get anyone in the department to know what they are if you need any help. But you can always email me. Have you got any questions about anything we said today? Or anything going forward? At this point, what we've done with previous cohorts, and it's up to you whether you want to do this, I leave you for now the 15 minutes remaining, or however long you want, to talk to each other. So you can basically chat now. I leave the room, take off my things, and you can chat about your experiences, how you find things, have you got any questions for each other, or just to share and chat. So you're free to do that if you like. Otherwise, thank you very much. I'll stop the recording now.